that would have been geometric. Because then I would have been able to rewrite that as 1 over e to the n, and that looks like an r to the n. That would have been geometric. Yeah?
Are you allowed to L'Hopital it and then?
No. Mm-mm. Yeah, you can't L'Hopital and then say, let's look at that series. You can only do the L'Hopital to figure out whether or not that sequence converges or diverges. So we don't have that, right? So it's not geometric. Is it harmonic? Harmonic? Constant over linear expression? No. Telescopic. Again, I don't see us pulling things apart and being able to get subtraction here anyway. So integral test, right, is the only thing we've got. So I'm gonna start out by first writing the function x over e to the x. Second thing, is it continuous on 1 infinity?
Yes.
Why?
Because I think for it to be discontinuous, trying to remove
X can never equal.
Yeah, this denominator can never be 0, because e to the x can never be 0. So this is always defined. We don't have any restrictions, so it's definitely okay on 1 infinity. So is it continuous? Yes. What's the next thing I have to check for?
decreasing, right? Or is that 4?
That's the 4.
Okay. There's a 0.
Positive, right? Is this a positive function? Is it above the x-axis? So is this positive when you're on the interval 1 to infinity?
Yes.
You know what? I don't know why I put n's. Sorry, x, e to the x. Definitely, right? Because look, the bottom is always positive, right? E to any number is positive. But then that's positive as well because I'm only looking between 1 and infinity for x. So that's definitely positive. One more thing, we need it to be decreasing. So to do decreasing, we take its derivative. What's derivative of that?
1 over, is it x?
That's a big old prime.
Or no, it is just the x.
Careful, you have to do quotient rule.
Oh, you do?
Yeah, you have a quotient. You can't just do top and bottom separately.
That's right.
No, L'Hopital is only to do limits, not to take derivatives, right? So quotient rule, which is the derivative of the top times the bottom minus the derivative of the bottom, which is itself, times the top, all over the bottom squared. E to the 2x. Good. I'm going to just write it this way, but you could rewrite that as e to the 2x. And we're wondering if this is always negative or positive, right? Or no, we want it to be negative, don't we?
Yes.
Okay, so let me look on top. Can't I on top pull an e to the x out of these two terms and get 1 minus x? And on the bottom, this is e to the 2x. See, these both have e to the x in them, right? So I pull e to the x out of both, and you get 1 minus x left in there? The question is this always less than 0? That's the question.
Yes, because there's going to be a negative.
Yeah, this right here is always positive. That right there is always positive. And this right here should always be negative so long as what? X is bigger than 1,
Yeah.
right? Which we're going to be going from 1, what, forever?
Yeah.
So look, worst case scenario, I plug 1 in. If I get 1, what do I get? 0. Okay, so at the very beginning, the slope of the tangent line is 0. But after that, what? It's decreasing, right? So that's good enough. We just need it to decrease as we go out. So we've got it. So now I do the integral. 1 to infinity, x over e to the x dx. How do we do that integral? Don't answer. I want everyone to think about it. Okay, raise your hand if you think you got it. You know, okay, anyone else? Who else thinks they know how to do it? Yes, yes? Okay. Maybe this will help for those of you who aren't seeing it. This might help. You don't have to do it this way, but you can. Did that help at all? Yeah. So what is it? You think?
It's voodoo.
Yeah, integration by parts. Integration by parts. So we'll need integration by parts for this, all right? I'm going to do it this way. I'm going to keep it in this form. So I'm going to let u be x, dv be e to the negative x dx. And now I differentiate here, I get du is dx. And I integrate here and I get negative e to the negative x. You have to have a negative here because of chain rule going backwards. And then we're going to do ultraviolet minus voodoo. I'm going to set that integral up over here without the limits of integration, do an indefinite integral. So ultraviolet minus the integral of voodoo. I'm doing a lot here, okay? I mean, just because we've been through this before, right? And we've done integration by parts before. There's a lot of little things with signs you have to pay attention to, right? These two multiplied is the front, and then minus, but we had a negative in the voodoo, so I brought that negative out, which made it a plus on that integral. And then e to the negative x was our v, and there's du. So this is voodoo here, but with the negative pulled out. And the antiderivative of that is itself, but with a negative again. So there's our antiderivative. I'm going to go one step further. I'm going to pull negative e to the negative x out and then be left with an x plus 1. I don't know why I did that, I just felt like doing it. They both have a negative, they both have e to the negative x, I just pulled it out. I mean, it can go even further. I don't know why. Just feel like it. I'm dropping it back down. All of these are the same thing, right? Yes?
So for the rule, it says it has to be integratable.
Integrable.
Integrable.
Mm-hmm.
So what does it mean if you can't? Like,
If you can't integrate it?
yeah, like.
Because you can't or because it's not integrable?
I don't know.
Well, I mean, it has to be integrable. Not all functions are integrable.
Oh.
Like, there are functions that are not integrable, just like there are functions that are not differentiable.
Have we seen?
I would not give you anything that's not integrable, though.
Have we ever seen?
We haven't really talked about integral functions that aren't integrable.
Okay.
Yeah. Unless there's like domain things, but there are functions that are not integrable even though they're defined on the entire domain. All right, yes? This is it, antiderivative, and now we need to do the limit thing for this. So this is the limit as t goes to infinity. And we've got the antiderivative, which is negative, then x plus 1 in parentheses, over e to the x, and we're going to evaluate that from 1 to t. And now we're just going to plug in. Plug in t first, then subtract when we plug in 1. We plug in t, we get negative t plus 1 over e to the t, and then when we plug in 1, we get negative 2 over e. Questions here? We're all good? Let t go to infinity. What happens here? Infinity over infinity? Negative infinity over infinity. So L'Hopital, right? L'Hopital. Do L'Hopital on this. Derivative of the top is what? Negative 1. So after L'Hopital, right, this will be negative 1 up top, and then what's the derivative of this? E to the t. And now run your limit again. You get negative 1 over infinity, which is going to be 0. So this whole thing goes to 0, doesn't it? And this does not.
Yeah.
This is just plus 2 over e. And isn't that just a number?
So, yeah.
And so this converges,
Oh, it's not.
right? This integral converges. So what does that tell you about the series? It converges too. Now, am I saying that the series converges to 2 over e? No, I'm just saying it converges. So therefore, the series converges.
So the reason it doesn't converge to 2 over e is because that's not the sum.
Yeah, remember how the rectangles had a little bit of like overlap and stuff? It was off. So we have some error in there, and that's why. And it's not easy to find that error. The test is not designed to find the actual area. It's just to determine the convergence or divergence. Okay. Next series test. The integral test is nice, but we're going to get a test. We're going to get this test that's coming, all right? We don't get it yet. We get this test in a little while, a couple of sections from now. And it's kind of like, you have this chest of tools, all these series tests. And it's like you got this series, you're going to go work on it, like trying to see if it converges, diverges. You're like looking around and you're like, you got this like one tool that takes care of almost every series. Not all of them, but a lot of them. And we're not to it yet. These are always going to be tests that we have as like a backup. Like it's like, okay, we'll use this one, we can't use that other one. It's called anyone know? Ratio test. It's called the ratio test. It's the almighty ratio. I call it the almighty ratio test. It's such a good test. But we don't want to overlook these because these are nice too. Like this one, P series. We're now going to look at a specific type of series. So this is almost like, harmonic was constant over linear? It's kind of the same idea. What if we have a constant over not linear, but n to some power? So like if that was n to the first power, that would be linear, wouldn't it? But if it's n squared, it's not linear anymore. If it's n cubed, it's not linear. So a P series is any series where you have a constant over n to some power. The P series stands for the powers, right? It's the powers of n. So it's 1 over 1 to the P, 2 to the P, or 3 to the P, 4 to the P. We have a very simple way of determining whether or not it converges or diverges. If P is bigger than 1, it's going to converge. If P is less than or equal to 1, it's going to diverge. So for example, if I give you this, does that converge or diverge? I'm not going to put 1 to infinity just for time's sake. Does that converge or diverge? Diverges. Why? You could look at this as a P series with 1, couldn't you? You could also say it's harmonic, but that's a P series, P is 1. And P is 1 means diverge. What if I do this? Converge. Why? P equals 2, bigger than 1. Converge. This is convergent. This one is divergent. Didn't we just do this problem? We just did that problem, didn't we? And we showed that it converged. We just did this problem. Like not just, but a few before. How did we do it?
I think,
How did we prove that?
did you do the integral test?
We did the integral test, right? You can actually prove, to prove this is true, you can actually do this integral. I'm not going to show it. If I have enough time in class, I usually do show this. But if you do this right here, if you do that and leave P as a variable and then do the integral, you can prove that this integral will converge, what? If P is bigger than 1 and diverge if P is less than or equal to 1. And once you do that for this in general, then you have this P series result. So we are taking the integral test to do this, and then from that we get this result, and we're just going to use the result. We're not going to go through a proof of it.
I think you did that proof earlier.
Did I? I think you're right. I think you're right. I think I actually did do that proof. I'm glad you remember that. How about this one? That's square root.
That's going to be
So what's P here? A half. And if a half is less than 1, right? And less than 1 is divergent. Well, less than or equal.
To be clear, that has to be the exact notation. Like it can't be like n to the p.
Good question. Good question. It has to be a constant over n to the p.
So yeah, no n to the p plus 1 minus 1, anything like that, right?
I think that's a good question that you might be able to answer yourself. What do you think?
Well,
Like this. Did you say p plus 1 or the n plus? Because if we add 1 to p, it's going to be a different p.
I didn't mean as a power. I meant n to the p and then like separately.
Oh, got you, got you. Okay, so this.
Yeah.
Okay, there we go. What do y'all think? Is that a p series? Is that exactly like this form? No, right? So this, we cannot say just by looking at that this is p series. We're going to need a test, a different test to be able to do this.
Wouldn't that be like what it harmonic, right?
No, because this is not linear down here, right? If that 3 is not there, then it's harmonic. But because it's third power, it's not.
You could factor, if that was plus 8, and you could sort of say the whole thing was, or I guess,
Like a,
if you could say that was sort of like a U sub situation where the whole thing was cubed, could you then do P series?
well, you would have to have one series with something, a constant over that thing to a p. You couldn't have multiple series. You couldn't have 2 different series. Because remember the whole idea of like they both have to converge. We're going to have a way of doing this. It's not going to be that hard to do. But we can't say that that's this case, I think is what your question was, right? Okay. All right. So do we need more examples? How about this? I'll give you another example of one we can't do. That's not a p series. If the 2 wasn't here, it's p series, right?
Yes.
With p being a half. But with the plus 2 here, can't do. Yeah.
Could you change the, I forgot how to word it, but could you change the notation where you change n to equal something else to where it cancels out the 2? And
Oh, so rewrite it.
For that particular one, you could, but the one above it, you couldn't.
yeah.
Yeah. Like you could change your index. Yeah, that would work. But we're going to have a test. It's called the comparison test. And it's going to be easy because what we're going to do is we're going to compare that to what we think it really looks like, right? Like this really looks like a p series with p equal 3. So I'm going to compare it to that. I haven't shown you how to do that yet, but it's the next test. All right. There it is. Y'all are asking good questions, but y'all are always like just like a step ahead of where we're about to go, right? So now the next test, the comparison test. So this usually takes students a few minutes to wrap their heads around. I'm going to try and see if I can do a decent job of doing it with my notes here. We look at another test now for convergence or divergence. It's called the comparison test. Let me just explain in words first what it's saying. We're given a series, all right? We're given some series. And I'm going to put an example over here. Let's do that one that we were just talking about. Was it 4? Yes. Yeah, okay. All right, so there we go. We're given a series, right? And we have a condition here. Whatever's here, that has to be greater than or equal to 0. So that is greater than or equal to 0, right? Positive always? All right, so we can use the comparison test. Now, what we do is we, the key word meaning we meaning you, need to try and find a similar series that you want to compare that one to. That's your choice. So I think a good candidate would be, I want to put it over here. I mean, I think these two almost look exactly the same, right? They're almost identical.
Yeah.
So our a sub n here is our a sub n, and then this right here is our b sub n. This was the series that was given, and here's the one that I have chosen to compare it to. And the reason I've chosen this is because they're so similar except for the plus 4, right? Yes?
I have a quick question. I don't know if I'm still reading it. If we had decided to do n to the 3 plus 5, would that have worked, or is that like too similar?
Hold on. Let me keep reading. Where is it? We want to choose a series to compare it to, right? We try to find a series to compare it to, which we've done, right? The series we choose to compare it to must be a series in which we know what it does. Okay? So you said, could we do what? N to the third plus 5. Do you know what that series does? You don't. Do you know what this series does? Why?
Because we have the p series.
It's a p series with p being 3. P is 3 is greater than 1. It's going to converge. So the thing you're going to compare it to better be something that you know what it does. Understand? Everyone good? Okay. So I've got this series. I don't know what it does. I've chosen a series to compare it to that I do know what it does. And now the critical thing. This is where you have to like see if you can wrap your head around this. This converges, right?
Yeah.
This converges. I'm going to put a C here. That converges. That means when you add that up, when you add all those things up, it goes to a finite number. This, when we add these up, we don't know what it does. But what if I could show you this, right? What if I could prove this to you? Let me get this out of here. What if right now, what if I can show you that A sub n is less than or equal to B sub n? What would you think if I could show that to you right now?
I was going to say, did you not say that a finite number plus a finite number is a finite number?
No, because these are different series. Yeah, let me keep going, because that's a road we're going to go off. Okay, we know what this does, right? We don't know what this does. But I'm telling you, what if I can now show you that this, right here, is always bigger than that? Any expression I have here is always bigger than that expression here.
Oh yeah, me too.
So if these guys are bigger than those guys, and these add up to be a finite number, then what must these add up to be? Finite number as well. It's like if I can show you that these are always smaller than those, then they should add up to be less than that. And if that's a number, then we're done. Right? So is it true? Is this true? Well, let's write down A sub n. Is this true? Question? Is that true? Yeah, how could you solve that inequality? You could just kind of like a cross multiply type thing, right? Where you just go like kind of like that and like that. You don't have to worry about flipping the inequalities over because these are always positive numbers. So as long as they're positive numbers, you can multiply both sides. So this is the same as n cubed is less than or equal to n cubed plus 4. But that's saying 0 is less than 4 or equal to 4. Subtract n cubed on both sides. That's true, isn't it? We're done. We now can conclude that this must converge as well. That has to converge. So maybe somebody else can explain it, because I've tried. Let me explain it one more time, and then we'll see if someone in the class can explain it to everyone as well. I have a series, I don't know what it does. I compared it to a series that looked very similar, but I know that this one converged. And then all I need to then do is show that that formula always stays smaller than that formula. And if I can show that, then I know that the sum of those has to be smaller than or equal to the sum of those, but this is a convergent number, so this is a number, and to be smaller than a number, you must be a number.
Yeah, because,
Yes?
So, is it like B sub n has to always be greater than A sub n? Or
No.
can it be the other way around?
It can be the other way around. You could have compared it to something that's divergent, okay? Which is, let's Before we go that route, does anyone have a question on what I did here? No?
I have a little question.
Yeah.
So the B sub n we decided to compare it to,
Yes.
do we have to know if it's bigger than A sub n?
No, you have to know that it's convergent or divergent. But it's important because that dictates the bigger or smaller. Watch. If this right here is convergent, then if this whole sum is convergent, then don't you want these to be bigger than those? Because what if it was the other way around? What if these were smaller than those? These would add up to be a number, and this would add up to be something bigger. That means it could be infinity.
Yeah.
You see, it doesn't restrict how big it can be. Does that make sense?
Yeah.
So what about this one? What about sum n equals 1 to infinity of 1 over the square root of n plus 2? Let's do that one.
So you could say it looks like 1 over n to the 1/2, right?
Yes, this looks like 1 over the square root of n. But again, we want to run through everything. N-term test fails, not geometric, not harmonic, not telescopic. Integral test? Could we do the integral test?
Yeah.
Probably. Shit, I don't feel like doing that though, right? I'd rather do a test that's going to go faster. So what I'm going to do is I'm going to compare it. Let me get this over here. I only have a few more minutes. So we're trying to find this. Sum n equals 1 to infinity of 1 over square root of n plus 2. All right, I'm going to compare it to sum n equals 1 to infinity of 1 over root n. This is a p series with p being a half, which does what? It diverges, right? Now I chose this because I think that this looks a lot like that, doesn't it? It looks a lot like it. So think about what we would need to show. If this becomes infinite, right? Then if I say that this is less than that, then that doesn't tell me anything, does it? Because you can be less than infinity and still be infinity.
Yeah.
So I would need to show that this is what? Greater than that. And that the only way to be greater than infinity is to be infinity yourself. So here's what I want to show. I want to show, whoa, my voice. I want to show that this one, that sequence, a sub n, is always what compared to this? Bigger, right? A sub n is bigger than or equal to b sub n. If I can show that that's true, then since this one diverges, that one would diverge as well,
Oh, yeah.
right? But I don't know if I can show this. It's not a guarantee. Is it? Does it work? Do y'all understand the inequality I set up? I'm asking myself, are these guys always bigger than these guys? If they are, then we have whatever this one does, that one does. Is it true? Yeah, try and do this thing, and what do you get? Root n greater than or equal to root n plus 2. Is that true?
No. Oh, wait.
Yeah, square root of 6 is bigger than square root of 4.
No, it's not.
This way, though?
You flipped it, yeah.
Isn't this number bigger than that number?
You could square both sides.
You could square both sides. But I don't think we even need to. This number is always bigger than that number, right? And the square root of that number should not be smaller than that, right? This is not good. This is not right. Do y'all see that? This is not true. So what does that mean? What we did is we looked at this, we said, hey everyone, we think that that looks like this. This is divergent. So in order to do a comparison, we would need these guys to be bigger than those, and that way that diverges as well. And when we tried to set this up, this wasn't true. What do you think that that tells you then? Do you think it tells you that that's convergent?
No.
It doesn't. This is like another failed test. That means that what you compared it to, you could not draw a conclusion from. So you need to use a different comparison or a different test.
Yeah, that's all I was going to say. I was gonna do the integral test.
we're out of, yeah, so maybe you resort to, no, there's another easier way. But let me put the actual test up here, like the formal notes for it. Let me see. You know what? Let's bring up your cheat sheets. So you can see it on there.
Yes.
Let's erase this. I've got 2 minutes. Give me just 2 more minutes. Let's recap what we've done here. All right, so what we've done here, nth term test, got it. That's the first test we tried. Geometric, got it. P-series, we just talked about. Okay, so there it is on there. Integral test, okay, it converges. If the integral converges, so does the series. Diverges if it diverges. And then over here is where it tells you, hey, remember, it needs to be continuous, positive, decreasing, and integrable. Then you have the comparison test. Comparison test says you have the thing you're starting with and the thing you're comparing it to. Let's say the thing you're comparing it to converges. Then you have to show that the A sub n's stay less than or equal to the B sub n's. As long as that holds, then they'll both converge. Now, if the B sub n thing diverges, then you have to show the inequality the other way around. You have to show that these A sub n's are bigger than the B sub n's, and then if they are, then they both diverge. This bottom part, ignore for now because we haven't done that. That's called the limit comparison test, which will come next class. We have not done enough of these to get going on it, all right? We need to do some more comparison, but just this gives you kind of a snapshot. We still need to do limit comparison, the almighty ratio test, the root test, the alternating series test, and we already did the last one. So we're getting through slowly but surely here, all right? So homework-wise, I don't even know. I'll have to email you. I have to keep you away from problems that require things we haven't done. Oh, you know what? I have it right here. I can tell you. I have the actual, oh, come on, stop doing that. The series, the homework. All right, here you go. Since y'all are right here, I'll tell you on the exercises what you can do from 8.3. Already? Someone jot it down for me, please. Numbers 6, 7, and 8 are all integral tests.